Okay, good afternoon, everyone. Okay, let's see. So just recently, good afternoon. Just recently, I was able to mark assignment 1, as well as I just posted some solutions to YouTube, so you could check those out under tutorials. Okay. And then today I'll post assignment 2, which will be due again in 1 week. It'll be similar, about 3 questions or something. Okay. And yeah. Okay. Today, what we want to do is look at some more examples of groups. And try and get used to calculations, like different types of calculations, like calculations with generators and relations and other things like that. Okay. So our kind of our motivating example is maybe the following problem. Okay. Let's find all groups of order 4. Okay. Well, what's happening to my video? Just a second. What's happening? Okay, sorry about that. So actually this problem, as I've written it, is kind of not so good. The reason is this is like a lot of different groups of order 4, but some of them look the same, right? So this is, I'll just say this is not a good question. The reason is, like, I might say, like, here's one group. E, A, B, C, and where we define like A squared equals B squared equals C squared equals E. And we say like AB equals BA equals C, etc. And then we also have another group, the group generated by A and, or I don't want to use A and B, the group generated by U and V, subject to U squared equals V squared equals the identity, and UV equals VU. Okay. These are not the same group, but it turns out they are isomorphic. So I don't want to find all groups of order 4 because I'll end up writing the same group in different ways a bunch of times. So what I really want to do is find all groups of order 4 up to isomorphism. Okay, so this is a bad way to write the problem, but a good way might be so like to revise the problem. Find all groups of order 4 up to isomorphism. Okay, meaning find a list G1, G2, and so on, such that any group of order 4, say G, satisfies G is isomorphic to GI for unique GI. Right? So like find a complete list of groups of order 4 such that any group is isomorphic to something on my list. Okay. Oops, sorry, someone. Yes, I can try to zoom closer. Is that a little bit better? Okay. Thank you for that. Okay. Okay, so right, so let's try and figure out what the groups of order 4 are. Okay. So a G be any group of order 4 okay. And what do we do? Well, there's two possibilities. Okay. Either there exists G such that the order of little g is 4 or not. Okay. Let me turn the page and remind you what the order of an element of G is. Just because that is something that will come up. Let me, right, reminder, or remember the order of G, that's the least positive integer D such that G to the D equals the identity. Okay, so if the order of G equals 4, that means that E, G, G squared, G cubed are all distinct. And when you compute G to the 4th, you get the identity. right? And you could ask, how do we know that these are all distinct? Right? Like, for example, how do you know like g cubed is not equal to g? Well, you just can do like some scratch work. If g cubed equals g, then we can cancel g's on both sides, and we get g squared times g equals e times g. Cancel g, well, you just get g squared equals the identity. That would mean that the order of g would be 2, but we've assumed that the order is 4. So that's not true. Well, that means like g cubed is different from g. Just as an example. Okay, so now if g has order 4, we can let h be the subgroup generated by g. Since these 4 things are all distinct, that's a subgroup consisting of these elements. So this subgroup generated by G has 4 elements. It's sitting inside G, which also has 4 elements. So we can say that like, since the number of elements of G equals the number of elements of H, and H is a subset of G, those 2 things together tell us that G actually equals H. So what that tells us is that if the order of G is 4 and the order of little g is 4 for some G, then G is a cyclic group generated by that element. Okay? And what happens now is that, well, all things that look like this are going to be isomorphic. Okay, so let's put that on our, like a little to-do list. Prove like that G and G prime, where G, the order of G equals the order of G prime equals 4, are isomorphic. Okay. Now there's another possibility. The other possibility is that the group G has no elements of order 4. Okay, second case would be that the order of G is less than 4 for all G and G. Okay. Okay. Now, we're still in the case that the order of the group has 4 elements. So this implies that G to the 4th is the identity for all the elements of the group. And this is by Lagrange's theorem, or you can just take it as given, but just to remind you, how do we show this? Well, you take H to be generated by little g, then the order of H is just the order of little g, but the order of H divides the order of big G, which is 4. Okay. This is by Lagrange's theorem, which says the order of a subgroup has to divide the order of the group. Okay. So the possible orders of the elements of G can be 1, 2, or 4 in this case. So let's record that. So for G and G, the order of G can be either 1, 2, or 4. If we have an element of order 4, then we're in the first thing we did. Okay, so we're crossing out 4. We're just considering the case that the order of G is 1 or 2. Okay. Now we just need to remember, if an element has order 1, what does that mean? There we go. If the order of G equals 1, that just means that G to the 1 equals the identity. In other words, yeah, it's only the identity. G equals the identity. Okay. So we know that in a group, there's only one identity. So out of my 4 elements, here's my group G. Has E has order 1. So we have G and order of G. E has order 1, and then I might have A, B, and C. Well, the only possible orders for this case are 1 and 2, and so these all have to have order 2. Okay, so if G has 4 elements and no element of order 4, then we have the other elements are A, B, and C, and A squared equals B squared equals C squared equals the identity. Okay. And now we just claim, you know, AB equals BA equals C. In fact, you might have done this before, but in fact, you can prove, let me put this as an aside. You can prove that the following statement, suppose for all X in G, X squared is the identity, then G is abelian. Meaning, that just means xy equals yx for all y and x. Okay. So this is just like a special case. Okay. So there's like some tricky way to prove this, but we can just kind of argue like, you know, the possibilities for A, B could be either the identity A, B, or C. Okay. If A, B is the identity, then we can multiply both sides by A. Then we get AB equals the A, which means, well, A squared is also the identity, so that means B equals A. Okay, but I've written out the 4 elements of G. So if A and B are really the same, that means G would only have 3 or less elements. So this is not possible. Again, if AB equals A, we can cancel the A to get B equals the identity. AB equals A implies B equals the identity. That means like E, the identity and B would be the same. Again, we would have 3 or less elements, that would be a contradiction. The same thing if AB equals B. If AB equals B, then A is the identity. That's impossible. So the only possibility is that AB equals C. Right. Now you can, so knowing that C is really A times B, and C squared is the identity. So AB is the identity. Now we multiply on the left by A. We get A squared BAB equals A, and A squared is the identity. So BAB equals A. And we multiply on the right by B. We get BAB squared equals AB. B squared is also the identity, so we get BA equals AB. Okay. So now my group has the form. So my group G looks like the identity A, B, and AB. And we have the rule that AB is BA. So now you can compute anything you want, because like if you want to do A times AB, well, you just do A times AB is A squared B, which is just identity times B, which is B. If you want to compute AB times A, well, that's just A times BA. BA is just AB. And A times AB is just A squared B, which is just B. Okay. Another way to write this group is that G is just generated by A and B, subject to the relations A squared equals B squared is the identity, AB equals BA. Okay. Okay, so this gives us, actually this like kind of completes our list. We're just gonna say, we're gonna claim that there's only 2 possible groups of order 4 of isomorphism. Okay. So let's call, define C4. This is going to be the group generated by A, satisfying A to the 4th is the identity, and define V to be the group generated by A and B, satisfying A squared equals B squared equals the identity, and AB equals BA. Okay, and then our theorem, let G be a group, order of G equals 4, then either G is isomorphic to C4 or G is isomorphic to V. Okay, and also, I guess that would only be part A of the theorem. But part B might say that V is not isomorphic to C4. Okay, so that tells us that really I have a complete list of all the groups of order 4 now. You give me any group of order 4 you want, well, it's really one of these 2 in disguise. Okay, so then I have a really good understanding of groups of order 4. Okay, so how do we prove this? Well, we just kind of follow along with what we were saying before, but we just try and condense things. Okay, So let G be a group of order 4. If there exists G and G with order 4, then we claim G is isomorphic to C4. Okay. So this is our first case that G has an element of order 4. Okay. Well, we just define phi from C4 to G by the rule, send the element A of C4, map it to the element G. Okay. Now, we've defined C4 by generators and relations. So that means if I want to know what is phi of any element of C4, all the elements of C4 are just powers of A. So if I want to know what is phi of A squared, well, I just compute phi of A times phi of A, and I get it that way. Okay. So phi defines a homomorphism if, well, when I plug in phi on both sides of this, I need to get an equation in G. So phi defines a homomorphism only when phi of A to the 4th equals phi of E to the 4th, which is just E. Phi of A is G, so only if G to the 4th equals E. But G is an element of order 4, so this holds. So G is an element of order 4, so that means phi defines a homomorphism. Okay, so now we have a homomorphism from C4 to my group G. It needs to be 1 and 1 and onto to be an isomorphism and to get this. So we just need to check is phi 1 to 1 is phi onto. Let's show phi is 1 to 1. Suppose phi of A to the n equals the identity. Anything in C4 looks like this. Looks like A to the n. Oh, the second to last line is A or G. This is an A. This is G. Before the tick. Oh, this is a G to the 4th equals the identity. Because phi, the definition of phi says if you plug in A, you get G. And G is our element of this like arbitrary group, and G has order 4. Okay. So if phi A to the n equals the identity, well, phi of A to the n, that's just phi of A to the power n. Phi of A is just G, so this is just G to the n. And our assumption is that, so our assumption then implies G to the n equals E. Okay. Okay, but now the order of G is 4, and G to the n is the identity. So that implies that 4 actually has to divide n. Okay, so let's write that down. So these two things together imply that n is a multiple of 4, or 4 divides n. Okay. In particular, if phi of a to the n equals the identity, that implies that 4 divides n, which it means if 4 divides n, that just means like if you write n is 4 times m, a to the n is just a to the 4m, which is a to the 4th m, which is e to the m, which is just e. Okay, so if phi of something in phi of a to the n is the identity, then a to the n is the identity. And this this shows phi is 1-to-1, which I want to explain after we take a little break. Okay, now phi goes from C4 to G. Phi is 1-to-1. So C4 and G both have 4 elements, and phi is a 1-to-1 function, so phi is also onto. That implies phi is onto. And then we conclude, so phi is an isomorphism. Okay, and then after a quick break, why is phi 1-to-1? And also, we'll finish the proof. Okay, so I'm going to end this meeting and just restart, and we'll start back again at 12:40. Okay, bye temporarily, everyone.